Thank you. Well done for getting through the alliterative title. And big thanks to Max for organizing all of this and for the invitation to come and speak. This is my favorite conference to come to. And it's usually in the middle of exam period, but I'm on sabbatical, so yay, I get to come. Yeah, so the session is about extraterrestrial and terrestrial remanence-carrying ensembles. And there's also a session later on in the meeting about machine learning. And I guess my presentation spans both of those topics. And what I hope to do is show you how machine learning can be the thread that connects microscopic observations about our samples at multiple length scales. So everything from the bulk scale, the bulk thin section scale there, to zooming in to and zooming in and zooming in to the sort of individual remanence carrying length scale. So microscopy, electron microscopy at multiple length scales, combined with multimodal imaging, so not just electron imaging, but also combining that with chemical mapping and EDS mapping and all of the sort of the rich mineralogical information that we can get from that. And then combining that with 3D multidimensional imaging, so not just the 2D imaging that we get from the SEM, but then going into 3D nanoscale imaging of particular regions of interest. And as I say, machine learning is a thread that combines all of these together to hopefully, the aim is to give us a kind of a complete picture of what on earth is going on inside our sample, right, in a quantitative way. That's the aim. And we've been developing workflows and bits of software to allow us to do that, which hopefully I will introduce. I should say, funding-wise, a lot of this work has been done through what's called the Excite network, which is a European-funded network for microscopy in earth sciences. And we lead a package within that network on machine learning. So a lot of what we've been doing is in that sort of field of microscopy and machine learning. But just to set up the context for this, and not my specific interest, so we're interested in the paleomagnetism of carbonaceous chondrites, which are really interesting materials. They're materials that formed reasonably far out in the solar system, early on, beyond Jupiter, it's thought. And so they were witness to the processes that were shaping the solar nebula in the sort of further reaches of the solar system. So we're interested in understanding the paleomagnetic signals that these materials carry so that we can quantify the intensity of the magnetic field that was there and understand the processes that were taking place. But doing this with carbonaceous chondrites is complicated. They're complicated materials. And there's a nice paper here that I'm going to use to set the context here. This is by James Bryson and Claire. What's Claire? Give us a wave, Claire. And Conal McNichol. And this was a paleomagnetic paper on the Winchcombe carbonaceous chondrite. But it illustrates the problems that we might deal with dealing with something like this. So if you think about a carbonaceous chondrite when it first forms, I can't see my cursor anywhere. So at the top, you have primary materials accreting into a carbonaceous chondrite parent body. So let's say you have metal grains and troilite, so iron sulfide grains accreting onto the carbonaceous chondrite parent body. For the sake of argument, we'll assume those grains are accreting in a random orientation. So the metal as a whole doesn't carry a bulk remanence. Those magnet moments are randomly distributed. And troilite is antiferromagnetic, so it doesn't carry a remanence. So that's your starting point. What then happens is you have aqueous alteration on the parent body, and that's going to alter those primary minerals. It may grow new ones, okay? So secondary minerals forming. So during aqueous alteration, that metal that you start off with metal, that gets converted into magnetite. And because the metal is magnetic and it's been converted topotactically into magnetite, it may inherit the pre-existing magnetic signal of those grains. And so because the metal wasn't carrying a bulk magnetization originally, when it turns to magnetite, it's still not carrying a bulk magnetization, right? Because it's more sensitive to the pre-existing magnetic state of the individual grains than it is to the external field that may be acting on it. So you have magnetite forming by oxidation of the metal, but not acquiring a remanence, basically. Whereas the pyrrhotite that's forming from the troilite during aqueous alteration is magnetized because it's forming from something that's antiferromagnetic. It doesn't have a pre-existing remanence that it can inherit. Okay, an alternative scenario on the right is that, that maybe some of that troilite got dissolved and reprecipitated as a different form of magnetite, framboids. We've heard a lot about framboids so far in this conference, which is handy because I'm going to be talking about framboids a lot here. So the framboid magnetite forms by precipitation from the pyrrhotite is dissolved, and then you precipitate magnetite. So it may be magnetized, okay? It's not inheriting anything. So on the right-hand side, you've got a situation where you've got two different types of magnetite, one which is not magnetized in the bulk and one that is, right? And so two different forms of the same mineral, but carrying different paleomagnetic signatures, okay? And you've also maybe got pyrrhotite and pentlandite in there carrying other signals. And then things get more complicated in the lab. You take that rock into the lab and you try and give it a laboratory remnants, and that magnetizes everything. Okay, and so you're comparing your natural remnants to a laboratory remnants, and they may not be carried by the same population of grains. Okay, so put it in the lab, you magnetize all of the magnetite in there and all of the pyrrhotite, but the NRM maybe only be carried by a subset. And so that really affects how you then quantitatively try and extract paleointensities. So the take home from that sort of schematic there is that you really care about your remanence-carrying ensemble if you want to do quantitative work and understand what's going on. And so there's a whole bunch of questions you might ask yourself about your sample, right? What's carrying the bulk remnants in my rock? Simple question, but an important one. How, when did that remanence-carrying ensemble form? And not necessarily the same question, how and when was that magnetized, okay? What domain states and interactions are present in the different remanence-carrying ensembles that exist within your rock? Do all the magnetic minerals hold NRM, or just a subset? And do all magnetic minerals acquire a laboratory remnants, or just a subset? Okay, that may depend on the coercivity of the particular grains and the field that you've applied in the lab. Okay. Now, this is all about the bulk magnetization, but within there may be micropaleomagnetic targets that you can focus on a small scale. So maybe you might focus on just the framboids and go, oh, what can we extract from those framboids individually, ignoring the bulk? So what paleomagnetic signals might those micromagnetic paleomagnetic targets carry, and how do we extract that? How do we interpret it? How do we quantify it, etc.? So this is a very long-winded way of saying that we really care about what's in our rock, both at the bulk scale, if we want to interpret bulk paleomagnetism, but also at the very fine scale. We need to know everything from individual particles and their properties all the way to the bulk level, and that's the challenge. Okay. Now, you might want to tackle this challenge using some kind of 3D imaging, tomography. We can do X-ray tomography of bulk samples. We can do very fine-scale tomography of bulk samples. But sooner or later, you come across the fundamental trade-off in 3D imaging, which is you can either image a wide field of view, a bulk sample, but with relatively poor resolution, or you can image a very, very small bit of your sample with very, very high resolution. You can't do both at the same time. There's always a trade-off. And unfortunately for us, we typically live in the gap of capability for 3D imaging somewhere between traditional X-ray CT imaging, where you can do centimeter-sized samples, but with maybe 1 micrometer resolution. Or you could do focused ion beam nanotomography, which I'll show you some results of, which are sort of a field of view of tens of microns and resolution of tens of nanometers, which is great, okay, but very limited in field of view. So we've been thinking of ways around this, and the simplest way is to not use 3D imaging, okay? The trade-off does not exist for 2D imaging. We can do SEM imaging at very high spatial resolution, and we can take those images across an arbitrarily wide field of view. We just have to take a lot of images tiled across the entire thin section, okay? So if you do 2D imaging, this problem doesn't exist, but you have another problem, which is if you do high-resolution images across a very wide field of view, you generate a lot of images, okay? That's a lot of data you have to deal with, quantify, and interpret. And that's where machine learning comes to your rescue, okay? You can't do this by hand. You need some way of automating this process, automating the acquisition of the data, automating the analysis of it. So that's the theme. And then we can do, once we have that bulk data, we can then do targeted, finer resolution things. So everything I'm going to show today is from this sample. It's a C2 ungrouped carbonaceous chondrite, WIS 91600. It's a sample that has had its bulk paleomagnetic measurements done and performed. So Bryson et al. 2020 did a bulk paleomagnetic study of this, found a paleo intensity of 4 microteslas. And that, if you use this sort of simple model of how magnetic field varied with distance in the solar nebula, as they nicely places this in the sort of beyond Jupiter part of the field. But that simple picture is being revised, mainly thanks to Kawe. But anyway, so it's been measured. It has a good paleo intensity estimate of 4 microtesla. And the reason it's quite a good measurement is because this carbonaceous chondrite was heated. So it's not just acquired a CRM during this aqueous alteration. It was then impacted, heated to 400 to 500 degrees C, and then cooled. So it carries either a full TRM or a partial TRM, depending on the magnetic minerals that might be carrying it. So we wanted to understand this material in much more detail. And so we've been doing a detailed microscopic study of it that tries to piece together all of these different length scales. OK. So the workflow overview is something like this. So we start with taking a whole bunch of SEM images across the whole thin section. So if you go to any modern SEM system worth its money these days, the ability to image high-resolution images automatically across your sample and stitch those together exists, right? So this is a relatively common way of working now. You can take individual image tiles. You can even do a chemical map at each tile now. And so you have a lot of data that you then have to process. OK, so if we just look at one of those image tiles, intensity isn't great, but you can see that the resolution is sufficient to identify different regions of interest within your sample. And what we then do is to use machine learning to isolate and identify automatically specific regions of interest. So the yellow outlines there you can see are these regions. These are referred to as magnetite framboids pseudomorphs after pyrrhotite. They've got these nice spherical particles of magnetite within these very distinct regions. And that defines one object of interest within these carbonaceous chondrites that we would want to identify and quantify. Okay? You can see other types of magnetite in there. There's framboidal magnetite here. Okay? There are other features like chondral fragments and that sort of thing. These are all features that we would want to identify and quantify in our sample. So we do that with machine learning. We then combine that with chemical mapping and then automated mineralogical analysis. So I'll show you a machine learning tool that we've published. It's a Python tool for taking chemical maps and doing an automated sort of breakdown of the spectra, unmixing those different spectra. And it's particularly aimed at our community because we're always dealing with very fine-grained things. We care about the fine-grained stuff that's on a length scale that is smaller than the interaction volume of our EDS spectra, right? So the challenge we always have to deal with is how do we work out the true chemistry of what we're looking at when we know that everything we're measuring is some kind of mixed signal from our EDS. Okay, so we have chemical mapping and mineralogical analysis, and then we go to, having got all of that data, we can identify what are the interesting regions that we need to know more about, and then we go to the 3D nanoscale imaging of specific regions of interest. Okay, so now we have detailed information about our remanence-carrying ensembles at this level, but we also know exactly where everything is in our sample at the bulk level. OK, so how does this work? So I haven't got time really to go into all of the ins and outs of machine learning and how it works. But the first task is a classic task for machine learning, which is segmentation, identifying and classifying different regions in an image. And the typical sort of architecture for doing segmentation is this convolutional neural network. And this particular one, UNet, is a very common one. If you do any sort of segmentation in machine learning, you'll come across UNet as probably the industry standard approach for doing this. What you need to do is you feed in to this neural network. At one end, you feed in each one of your images. That then is taken through a series of convolutional steps which reduce the size of that image gradually, so building up sort of bigger and bigger scale information. And it also, at the same time as reducing the size of the image as we go down this path, it increases the number of layers of feature information that it finds about the sample. So by the time you get to the bottom here, you have a very small image, but a whole stack of information about the features within it. You then have to then expand that back out to the full size. And so through this expanding path, you get back to the full size. And what gets spit out at the end is a classification of different objects. And these arrows across the top, these are called skip connections. This is a way to, obviously, as you go down that contracting branch, you're losing a lot of information as you reduce the size of your image. Which you then have to try and get back as you expand. Those skip connections blend the very low-level information and the very high-level information at each level, so you retain information about your sample on all scales. And then you train that network to classify what it's seeing into any number of user-defined objects. Okay? In this case, we've chosen 7 objects. So we've got class 1 chondrules, which are these sort of dark regions. Okay, class 2 chondrules, which are the lighter ones up at the top. Coarse, isolated magnetite particles, sort of in the upper right of that image. Framboidal magnetite, which is this sort of stuff here on a very fine scale. The matrix, which is the phyllosilicate matrix that makes up a big proportion of the sample. These magnetite pseudomorphs, which are these distinct features here, and then coarse sulfides. So you can see just the bright stuff around that type 1 chondrule at the top is coarse sulfide. And the output of this UNet classification thing is a sort of a depiction of where each of those features is. But to do that, we've had to train it. Okay, so we've had to give it some training data. We've had to manually draw around a certain number of these features. Okay, so the amount of training data is 1.3% of the total number of pixels in the data set. So the 1,290 images, of which 1.3% of the pixels in those images were labeled. It's equivalent to about 16 images that we've had to manually label. It's actually not as bad as that, because if you look at the percentage of your sample, of your training data set, which is matrix, 66% is matrix, right? So you don't have to draw that. You just have to draw everything else and then tell it everything else that I haven't labeled is matrix, okay? So actually, it's only about 6 images worth of segmentation. And since developing this approach, we're now getting around to any kind of manual training by using the chemical segmentation that I'll show you in a second. So there's a way to get around this so you don't have to do any manual segmentation. We can just use the automatic segmentation that the chemical mapping tells us, and then we can feed that in. Okay. So what do you get from that? So once you've given the training data, you've trained the network, you classify all these objects, you then get a breakdown of how much of each of those objects is in your bulk sample. So how much is chondrules of different types, how much is coarse isolated magnetite, how much is framboidal magnetite, 7.3%, quite a lot. How much is matrix? So 75% of the sample is matrix. And these weird pseudomorph things here are 1.4%, and there's 0.4% coarse sulfide as a bulk breakdown. And the important thing to point out here is, A, there's a ton of magnetite in this carbonaceous chondrite, but B, with segmentation, this is different to what you would get from XRD, right? XRD would tell you have a certain amount of magnetite, but here we're differentiating magnetite of different types based on their texture. Framboids are different to these features, which are different to the isolated magnetite, and we get a breakdown of that on a textural basis, right? So that goes back to the problem we were dealing with at the beginning. Like, we want to know not just how much magnetite is there, but how much of different types of magnetite are in your rock. Okay, so what else can you do with that data? So you can use it to start doing particle analysis at the bulk scale. So we start with taking one of our images, apply an image threshold to that to highlight the bright stuff. Now that includes everything, sulfides, magnetite of all different types, iron, metal, everything, okay? So you normally can't do anything with that, but now we have the map of where all our different types of magnetite are. We just intersect the two, and we can say, okay, just show me the magnetite that's inside these weird pseudomorph things. Okay, that does that across the whole sample, and then we take that apply something like a watershed transform just to isolate the individual particles, and then you do your particle analysis, okay? So that's 2 clicks of a button in ImageJ to get from there to there. And then you've got your sort of breakdown of particle size distribution of the magnetites that's just inside those specific features, right? And of course, we can look at the particle size distribution of the features themselves if we want to know, how big are these pseudomorph regions in total and where are they in the sample. You can get your breakdown, your particle size distribution of the pseudomorphs themselves, and then also the magnetite that's contained within them, right? So you're getting aspect ratio, size information on a very specific type by type basis, I guess, is trying to get the point across. So we can do that sort of thing with the chondrules, which have camosite in them. We can just say, OK, just show me the chondrules, highlight the iron camosite that's inside the chondrules, and tell me how big they are, for example, right? We can do those, play those sorts of games. So next, I want to talk about the chemical mapping side of this. So once there's a limit to what you can do with backscattered electron imaging, right? Right, that just gives you intent brightness, OK? It's not very discriminatory. What you really want to do is chemical mapping. And what we've done, very often what we find, and looking at the presentation so far, any number of examples of where you're dealing with chemical mapping of samples which are very fine-grained. So the features in your sample are smaller than the interaction volume of your EDS. And so you're struggling with, OK, well, how do we treat chemical mapping data of very fine-grained things in an automated way? So Sigma is a tool that we've developed in Python. The new version of this is about to be released, which is all very GUI-fied and interactive. But it's designed to do several things. Basically, take our stack of elemental maps, do an automated cluster analysis of the different sort of regions of interest, different chemical things, and then unmix those spectra to give us the fundamental chemistry of the individual phases that are present, okay? So you take your chemical maps, you identify clusters of chemically similar things. So this is chemically similar to this. So they would appear as one cluster. But each of those things is 2 phases. In this case, it's this phase plus the matrix in both, right? So although these are part of the same cluster, they're not single phase. They're 2 phases. And you want to know what the individual phases are. So Sigma will do both this clustering thing and then the next step, which is then to unmix and tell you what the individual phases are. That's the idea. So how does it work? So as in most machine learning, you start with some kind of high-dimensional data. So in our case, the high-dimensional data is our 2D chemical maps, which then are a stack of all the different elements that we're interested in. So you might say, OK, 10, 15 elements. That's a 10 to 15 dimensional data set. And we have that information for every pixel in our image. OK, you then need to do dimensionality reduction to make sense of that. So we can go from a 10, 15 dimensional data to just 2-dimensional data that we can plot out. And there are lots of ways of doing dimensionality reduction. We've seen several already today. PCA, as we've mentioned several times, which is a very common matrix-based linear way of doing dimensionality reduction. We're using a machine learning, highly nonlinear, but very effective way of isolating and doing this dimensionality reduction. We use either autoencoder, which is a neural network approach, or my personal favorite at the minute is UMAP, which is a graph theory-based approach of dimensionality reduction. Seems to work beautifully with chemical data. OK, so the idea is take your high-dimensional data, reduce it to 2 dimensions, then all of your phases should appear as individual clusters within that latent space, as we call it. You then use any number of clustering algorithms to identify the clusters. So there's 2 built into Sigma, Gaussian mixture modeling and HDB scan, which are both very good at slightly different things. So often using a mixture of the 2 works really well. Once you've identified your clusters, you can then calculate the individual chemical spectra of each of those clusters and then plot out the phase map. And then there's a next stage, which is to take those spectral maps and then do another layer of unmixing to find out the fundamental phases that are present. Because each of these spectra is almost certainly a mixture of multiple phases when you're dealing with very fine-grained things, right? Okay. So an example. So here's a nice interesting feature in our carbonaceous chondrite containing multiple different phases. There's magnetite in here. There's sulfides, 2 different types of sulfides. There's the phyllosilicate matrix, and you can see the matrix contains very fine-grained additional phases within it, which are below the resolution of the EDS mapping. So the input data is our chemical mapping. So we've chosen these 12 elements of interest to put into the algorithm. We do the dimensionality reduction to get our 2-dimensional latent space. So that's over here. And you can see this kind of blobby thing with, largely 3 bits to it, and then this thing here, and then this kind of green thing sticking out. Okay. So I've deliberately over-segmented that. So I fitted 20 Gaussians to that just to give us a patchwork subdivision of that latent space, which samples the different chemical heterogeneity. And if we just take those colors and plot it here, we can see how that gets divided into this map. You can see these colors are picking out this sulfide rim. The red and orange and purple are picking up the magnetite. This green thing sticking out here is something distinct. Okay, and then you've got the matrix phase here, which you can see there's chemical heterogeneity in there. There's regions that look more blue, the regions that look more green, and that's because there's chemical variation within the matrix. So using our software, you can sort of interactively sort of select these clusters and merge them or color them in order to make this sort of more simple and useful, okay? And then you can start to label these things. So this big pink blob here is the matrix, and that big spread is because of the chemical variation within the matrix that exists. The red here is now magnetite, and the bit I've colored orange is where the magnetite has reacted with the aluminum, get me, I'm in the US, aluminium, reacts with the aluminum polishing material to form personite. Okay, right. So that's kind of a bit of a sample preparation artifact that it picks up. It's picked up these little green things here, which are these chromium manganese regions. So chromite, spinel, and then it's picked up these 2 different flavors of sulfide. Okay, so each of those regions you can then get your spectrum. That's the phyllosilicate matrix, magnesium silicon, with a very small amount of sulfur and iron mixed in there. That's our magnetite, which are those plaquettes in the center. This is the aluminum-rich region here. You can see the aluminium peak. We've got 2 different types of sulfide. So one has a distinct amount of nickel in it, okay, which is blue, and then the other bits have no nickel in at all, and there's a yellow, and you can see the heterogeneity in that nickel-bearing and non-nickel-bearing sulfides in that sort of rim that's going around that grain. And then these are the chromite regions. So you've got chrome and manganese, but you can also see other elements here, silicon, magnesium, sulfur, iron, and those because these chromite grains are very small, so you're still getting mixtures from the matrix and that kind of thing. So this is not yet unmixed into the fundamental phases. That will be the next step. So the next step is to take those cluster spectra and then run it through what's called a non-negative matrix factorization. And that basically says, okay, I'm going to approximate this sample as 3 phases, let's say. You choose that number. I think there's mainly phyllosilicate, magnetite, and sulfide. Those are the 3 I'm interested in. So let's specify 3 phases. It's going to take all those clusters that I originally defined. So I usually use about 50 to do this. Feed that through NMF and ask it to produce the 3 fundamental spectra that it thinks are there and the proportions of each of those spectra in the actual data. Okay, so this is what that looks like. So it unmixes the cluster spectra into these 3 fundamental spectra, which are the phyllosilicate, pure iron sulfide with a little bit of nickel in there, and pure magnetite. And now it can then tell me how much of each of those 3 components is in each of those 50 clusters that I defined. So we get a quantitative mixture now of how much matrix, magnetite, and sulfide is in each of those clusters. And if you restrict yourself to just looking at the matrix bits, you can then work out roughly how much magnetite, and sulfide is mixed in at a fine scale within that matrix. Okay, so here I've just selected out just the matrix points, and you can see that it's predominantly sulfide rich. So most of the matrix has fine scale iron sulfide in it, but there's also some magnetite there, but it's predominantly matrix. So we're starting to get a quantitative breakdown of the contents of the matrix. A good way to view that is this RGB way. So blue is the magnetite, green is the sulfide. The matrix is a mixture of red, green, and blue, and you can see regions which look more purple and regions which look more brown, and that's the chemical variations in the amount of iron sulfide and iron oxide contained within the matrix at a fine scale. Okay. So that's everything in terms of 2D. We have a bulk breakdown from the backscattered electron images, the 2,000 images taken across the entire sample. We can understand what it is we're seeing with EDS. We can take those EDS segmentations and now use that as training data for the first stage. And then the next thing is to look at individual regions of interest and say, okay, well, let's now characterize at very fine detail the magnetic properties or the magnetic particles contained within certain regions. So for this, we're using slice and view nanotomography. So using a focused ion beam, you basically slice your way through a volume of interest. So on the top here is platinum that you've deposited on the surface to protect it. Those dark bars are carbon deposited on the top to act as fiducial markers so that you can align the images. Okay, cool. And yeah, so using a focus ion beam, you slice through the sample sort of 20 nanometers at a time. And if you walk past the physics building between where we're staying and here, you'll walk past two beautiful artworks, which are a perfect illustration of slice and view in action. There's a man and a woman made of metal slices in 3D. So look out for those, because it's a perfect illustration of how slice and view works. So the length scale here is about 40 microns, 20 microns by 20 microns. That gives you a sense of the sort of volume you can reconstruct. And what you do with that data is then you put all of these thousands of images through the machine learning to do the segmentation. Okay, so you don't have to do that by hand anymore. And it then spits out, images like this. So we can reconstruct the three-dimensional information inside that volume. So we have these framboids, magnetite framboids. The green here is carbonate, iron, magnesium, calcium carbonate, which contains magnetite within it. These regions are matrix containing that fine-scale iron sulfide that we discovered with the EDS. Okay. You can then take these sorts of regions, do a watershed segmentation to identify the individual particles within there. Okay, and what we find we find that these particles are pretty well uniform. They're about 500 nanometers in size, aspect ratio of 1, and a packing fraction of 74%, right? So this is a close packed array of 500 nanometer size spheres of magnetite, okay? You can then, if you want to really burn some computer time, is simulate that thing. So this is a close packed array of 500 nanometer size particles, starting from a saturated state. So uniform magnetization, and then say minimize the energy. And what you find is that everything turns into a beautiful vortex, and those vortex cores are all randomly arranged. And your remanence is tiny. 0.0031 is your saturation remanence of a framboid like that. So that gives you an idea of the stuff that you found and actually how it behaves. So we can feed that into micromagnetics. Okay, and then we just do lots of pretty pictures. So yeah, framboids, plaquettes, and you can see the close packed nature of the framboid using this thing. You get the 4 1-1-1s planes here. So you can start to see the symmetry, the fourfold symmetry of this thing. Okay, so these are very highly organized collections of very well-defined particles. But are they significant magnetically, paleomagnetically? That's the big question. So yeah, another pretty picture. More pretty pictures, okay? This one is interesting because we're focusing here actually not on this beautiful plaquette, which is a bit of a distraction, but on the matrix around it. which is filled with pyrrhotite, as we've seen from the EDS. Additional evidence that it's pyrrhotite, we can find this little particle here highlighted in yellow. It's this perfect hexagonal morphology. So you can show from the morphology that it's probably pyrrhotite. You can get a complete breakdown of the size and shape distribution of those pyrrhotites. And it's filled with, this is the single domain size range for pyrrhotite. So your matrix is filled with beautiful, highly spaced, non-interacting single domain pyrrhotite. Awesome, right? And then finally, you can start to play some quantitative games. You can say, well, okay, what is the total remanence-carrying potential of the matrix versus, say, the total remanence-carrying potential of rhomboids? Now, from our bulk analysis, we know exactly how much of the sample is matrix and how much is rhomboid from our machine learning segmentation. We know from the EDS what the main carrier is, pyrrhotite in the matrix, magnetite in the rhomboids. We know how much is in the how much of the pyrrhotite is in the matrix from our 3D, which is 3.4%, is the pyrrhotite. We know it's single domain, weakly interacting, has an MRS over MS of something like this, an MS of that, probably a full TRM, because this thing was heated above 320 and then cooled down. So that gives you a sort of a estimate of how much remnants could the matrix hold. And if you compare that, you do the same for the rhomboids, which are these seductively beautiful things. 7% of your sample is rhomboid, but its remnants carrying potential is negligible compared to the matrix, right? And mainly because of this micromagnetic simulation that tells us these things do not hold remnants. They disorder very quickly. So I'll finish there. I mean, so the conclusion is, in this particular case, we were interested in answering this question, like how much of the bulk remnants is carried by the matrix versus other stuff that's in there. And I think the answer comes out very clearly that the matrix is the dominant carrier of bulk remnants. But that doesn't mean you can't do a micropaleomagnetic measurement of the rhomboids and see if there's any information there or any of the other features that you found in there. OK, so hopefully that's giving you some idea of what we can do in the sort of combination of microscopy and machine learning. I'm happy to show anyone Sigma. I've got it running on my laptop. If anyone wants to have a look at it, I'm happy to demo that to anyone. And with that, yeah, I'll finish. Thank you.